Hello everyone. Today in this lecture we will see how to are the details of the standard image compression. So that is here JPEG. The standard one of the image compression is in JPEG compression technique. So these are the different modules inside of this particular JPEG encoding only. So here we will see the encoding part, and the decoding part is an exactly opposite operations which will take place inside the decoding part. So the first part we need to divide that whatever the image we are going to compress, that image need to divide it into blocks. So in the standard JPEG compression they are using 8x8 blocks. So we'll see that block diagram later. So the steps involved in this JPEG are DCT, discrete cosine transform, quantization, zigzag arrangement, run length encoding, and DPCM. Next one is an entropy coding. So here basically in the JPEG standard image compression, they are following the Hoffman encoding method in order to get the standard compressed data as an output. We'll see one by one how that each and every step is going to uh, happen inside the JPEG compression one by one. So why first of all this JPEG compression important? Why we need to choose this JPEG compression? So why this JPEG compression important? Actually, there is a lot of different kinds of compression methods are there. So in terms of lossless mode, that means here lossless mode in the sense there is no difference between the compressed one and the standard image. So with the help of Hoffman encoding and then LZW, that is Lempel-Ziv algorithm. So these are the different kinds of lossless mode of compression methods, but these are not high enough for the image and video compression. Due to that reason, we are going for the JPEG compression, where there are two factors are there why I have chosen this JPEG compression. In the sense here, the human eye, it is immune to loss of higher spatial frequencies and then than that of the lower frequency components. That means that means human eye can't recognize the losses happen at the higher spatial frequencies. It is possible to recognize the errors present in the lower frequencies only. So that is one of the reason why you have chosen this JPEG compression mode. And the next one is in lower spatial frequencies having a higher in terms of more lower spatial frequencies are having the higher information components, which means that, so if suppose I can divide, this is a one box. So here this is a lower frequency bound, this is a higher frequency bound. So where this lower frequency bound is having the more amount of information regarding the image, so where this higher frequency side is having lesser amount of information. If you discard this also, our human eyes are not able to recognize this one. So due to these are the two facts why you are choosing this particular JPEG compression here. Okay, so this is a block diagram of the JPEG encoding part. So here we can consider this is an image. This is an image block where which we are having the three channel here. So three channels we can call it as a grayscale image also, like a grayscale image. Whatever the image you want, we can compress here. Three channels. This is we need to form these operations throughout that one. Chrominance and eliminance blocks. So here we are dividing entire image into 8x8 blocks. That is calling here it is an f of I comma j. So which represents the two-dimensional array. So on that we are performing the two-dimensional discrete cosine transform on that 8x8 block. After that, so here what will does in the sense in the discrete cosine transform, it will place higher amount of information at the lower frequency side. Here if you say this is a lower bound, so here it will place the higher amount of information, where when compared to these are the higher higher frequency components. So here we may have the lesser amount of information, like which is having the less priority of that particular image. So that means here this particular discrete cosine transform will transfer that pixel intensities into frequency domain. So in the next we are going to we are going to compress the particular discrete cosine coefficients into some other format by using the quantization, where in the standard JPEG compression mode, where they define some quantization table, standard quantization matrix. So based on that, we are dividing this particular, whatever the coefficients we are getting, those coefficients are individually divided by the each element presented here. If suppose this is an 8x8 block, so this is an 8x8 matrix, suppose let it be 8x8 matrix. So the standard JPEG compression defines some tables like 8x8 matrix in terms of. So here if I consider the first element, this first element is divided with the first element presented here. That means we are dividing f of u comma v divided by this particular, we can represent this is an q, we can use q. So here we can write qi comma j. So whatever the value we'll get it here, the next one we are going to store those values corresponding locations on. In the corresponding location we are going to place those, that particular divided value we are going to place it over there. So that is where we are getting the loss of information where. So here after completing this particular discrete cosine transform, we'll get most of the higher element, higher frequency locations will get the very least capacity of information. So whenever you are dividing with this quantization matrix, almost those values reaches to 0. So based on that we can say that the maximum loss occurring in this quantization step. Okay, and next that particular quantization output is passes through this particular DPCM and then run length encoding. So here we are transferring that particular quantized output, whatever the matrix we will get it here, 8x8 block matrix. The first value here, the first component present in this matrix, that is called here DC component. DC component. That particular DC component is passes through this particular DPCM, differential pulse code modulation, which means here it will calculate the difference between this particular one, this particular DC component and the previous value. So that one will store it in the, that one will pass it through the entropy coding. And next whatever the remaining values are there here from here to last, that one will pass it through the run length encoding. Will in the next subsequent slides we will see how to define this run length encoding and the differential pulse code modulation. And next after completing these two steps, the outputs are applied as an inputs to the entropy coding, where here we can use the Hoffman encoding step in order to get the compressed data. That one can be defined by using some coding table. We'll see all those details in the next video.